light leaves Earth at the fastest speed anything in the universe is allowed to move. Yet even then, it needs more than 4 years to reach the nearest star beyond our Sun. And at that same relentless pace, it would take 100,000 years to cross the full width of the Milky Way. These numbers are not poetic exaggerations. They are cold measurements that define the boundaries of human reach. They reveal an uncomfortable truth that we rarely sit with for long. We are not just far from the stars, we are effectively cut off from them. The universe has wrapped humanity inside an invisible cage built from the laws of physics themselves, where distance becomes punishment and time becomes an enemy. Every dream of interstellar exploration crashes into the same barrier, the simple fact that space is too large and we are far too slow. But what if that cage was never truly solid? What if the bars were not meant to be broken, but bent, reshaped, or quietly stepped around? Over the past few decades, physicists have begun uncovering ideas that sound less like science fiction and more like loopholes hidden deep inside reality's rulebook. These ideas suggest that spacecraft might not need to race through space at all. Instead, space itself could be persuaded to move. If correct, journeys that once demanded tens of thousands of years could shrink to years, months, or even weeks. Concepts once dismissed as fantasy laboratory-created warp bubbles, gravitational signals that might betray the movement of advanced civilizations, and energy requirements that fall from outright impossible to merely staggering are now discussed in serious scientific papers. We are standing at the edge of a moment where the definition of travel itself may change, and where the universe might finally stop laughing at our ambitions. To understand why this matters, we must first confront just how deeply trapped we are. Humanity's fastest spacecraft ever launched streaks through space at a speed that sounds impressive by earthly standards. Yet it would still require tens of thousands of years to reach even the closest star. The Voyager probes, launched in the 1970s and now billions of miles from Earth, have spent nearly half a century traveling outward and still remain bound to the Sun's gravitational influence. In cosmic terms, they have barely crawled beyond the front yard. Every star visible in the night sky represents a destination that, with current technology, might as well exist in a different universe. This is not due to lack of effort or imagination. We have built machines capable of surviving radiation, vacuum, and extreme temperatures. We have landed robots on distant planets, flown past icy moons, and photographed galaxies billions of light years away. Yet despite all this progress, our physical reach remains shockingly limited. The problem is not engineering skill, it is scale. Space is not merely large, it is structured in a way that actively resists traversal. Distances between stars are so immense that even traveling at a significant fraction of light speed would still demand voyages lasting longer than human civilizations typically survive. This creates a paradox where knowledge outpaces ability. We can measure the atmospheres of alien planets, detect water vapor around distant suns, and calculate orbital periods with astonishing precision. Yet we cannot send even a small probe to verify those discoveries within any meaningful time frame. The universe allows us to see almost everything, but touch almost nothing. This is why the idea of faster-than-light travel is not a childish fantasy or a luxury reserved for speculative futures. It is a direct response to a fundamental constraint that defines humanity's place in the cosmos. Without a way to overcome this constraint, We remain a single-planet species balanced on a fragile world, vulnerable to extinction-level events we cannot always predict or prevent. Asteroids, climate instability, stellar evolution, and cosmic radiation do not care about human timelines. If Earth becomes uninhabitable, there is no nearby refuge waiting for us. Every potentially habitable world lies light years away, separated from us not by courage or ingenuity, but by physics itself. This reality has forced scientists to ask questions that once seemed unthinkable. Instead of asking how to build faster engines, they began asking whether motion itself has been misunderstood. Instead of pushing harder against the universe, they wondered whether the universe could be persuaded to carry us instead. These questions mark the beginning of a quiet revolution in physics, one that challenges the assumption that humanity must forever crawl between the stars. The journey ahead is filled with uncertainty, skepticism, and enormous technical challenges. But for the first time, the prison walls appear to show stress fractures. And if those fractures can be widened, even slightly, the future of human exploration could change forever. Once the emotional weight of our confinement sinks in, the raw mathematics of distance makes the situation even more unforgiving. Because space is not just vast in a poetic sense, it is structured in a way that turns even optimistic travel scenarios into exercises in futility. The nearest star system beyond our Sun lies more than 4 light-years away, a gap so enormous that light itself, the fastest messenger the universe allows, requires over 4 years of uninterrupted travel to cross it. For any spacecraft built by human hands, that distance balloons into a timescale that exceeds recorded history. Even if we imagine a probe moving faster than anything we have ever constructed, the journey would still take tens of thousands of years, long enough for continents to shift, languages to disappear, and entire civilizations to rise and fall. When we zoom out further, the numbers become almost absurd. The Milky Way spans roughly 100,000 light-years from end to end, meaning that even a signal traveling at light speed would need 100 millennia to traverse our own galaxy. To put that into perspective, modern humans have existed for less than 3% of that time. Agriculture, cities, writing, science, and spaceflight all emerged within a tiny sliver of that span. The galaxy operates on a timeline that renders human ambition microscopic. This is why our achievements, impressive as they are, feel strangely fragile when placed against the cosmic backdrop. The Voyager spacecraft provide a sobering illustration. Launched in 1977, they are among the fastest and most enduring machines humanity has ever created. After nearly 50 years of continuous travel, they have crossed billions of miles and entered interstellar space. Yet they remain astonishingly close to home by galactic standards. They have not reached another star, nor will they for tens of thousands of years. Their journey highlights a brutal reality. Even our most ambitious missions barely dent the distances that separate stars. Every improvement in propulsion yields diminishing returns, because the scale of space grows faster than our ability to cross it. This is not a problem that can be solved by patience alone. Waiting longer does not help when the required waiting time exceeds the lifespan of civilizations. Generational ships have been proposed as a workaround, massive vessels where entire societies would live and die during the journey. But these concepts replace one impossibility with another. Maintaining stable social structures, technological continuity, and biological viability over thousands of years introduces risks that compound until failure becomes almost inevitable. A single catastrophic event, cultural shift, or loss of knowledge could doom the mission long before it ever reaches its destination. Even robotic probes face similar issues. Components degrade, power sources decay, and unexpected conditions accumulate damage over centuries. Space is not a benign void. It is filled with radiation, dust, and subtle forces that slowly erode anything passing through it. When distances stretch into tens of thousands of years, even the most carefully engineered systems begin to look temporary. The tyranny of distance is therefore not just about how far stars are, but about how time weaponizes that distance against us. The longer a journey takes, the more opportunities exist for failure. And at interstellar scales, those opportunities become overwhelming. This explains why humanity's exploration has remained confined to its immediate neighborhood despite decades of progress. We have mastered short hops across the solar system, but every step beyond that feels exponentially harder. The jump from Earth to Mars is trivial compared to the jump from the Sun to the nearest star, not because of courage or funding, but because the universe has arranged itself in a way that punishes linear thinking. Doubling speed does not halve travel time in any meaningful way when distances are measured in light years. It merely shaves off a small fraction of an otherwise unmanageable timeline. This reality has shaped how we imagine our place in the cosmos. For most of human history, the stars were symbols rather than destinations, unreachable lights fixed to an eternal dome. Modern astronomy replaced myth with measurement, but the conclusion remained eerily similar. The stars are still beyond our physical grasp. We can catalog them, analyze them, and watch their evolution, yet remain spectators rather than participants in the galactic story. This creates a deep tension between what we know and what we can do. As our telescopes grow more powerful, the universe feels closer intellectually, but farther physically. Each discovery of a promising planet or nearby star system intensifies this frustration, reminding us that knowledge alone does not grant access. Without a radical shift in how we approach movement through space, the vast majority of the galaxy will remain permanently out of reach, no matter how advanced our instruments become. The tyranny of distance is therefore not an abstract concept, but a defining feature of human existence in a universe that seems almost intentionally structured to keep its wonders just beyond our reach. Faced with distances that dwarf human history, it is natural to assume that the solution lies in building better engines. Yet every conventional propulsion system ever designed runs headfirst into the same unforgiving limitation. All rockets, regardless of how advanced they appear, rely on a single ancient principle. To move forward, something must be thrown backward. Chemical rockets burn fuel and expel hot gas. Ion drives eject streams of charged particles, and nuclear concepts heat propellant to extreme temperatures before blasting it out the rear. The details differ, but the physics is identical, and that physics becomes a trap when travel times stretch beyond the solar system. As speed increases, the amount of fuel required rises dramatically, and that extra fuel adds mass, which in turn demands even more fuel. This feedback loop is not an engineering oversight. It is a mathematical certainty known as the rocket equation. Engineers can tweak designs, optimize fuel mixtures, and invent clever staging strategies, but none of these tricks change the underlying relationship. Carry more fuel, and the vehicle becomes heavier. Make it heavier, and you need even more fuel just to accelerate it. At interstellar scales, this spiral becomes catastrophic. The vehicle rapidly turns into little more than a flying fuel tank, with the payload shrinking to a negligible fraction of the total mass. Eventually, adding more fuel stops increasing performance at all, because the energy spent lifting the fuel outweighs any gain in speed. This is why even wildly optimistic propulsion concepts struggle to approach meaningful fractions of light speed. The faster you want to go, the more brutally the math pushes back. It is tempting to imagine that future technology will simply overcome this problem. But physics is not impressed by optimism. Chemical rockets, the workhorses of spaceflight, are already operating near their theoretical efficiency limits. Ion drives are far more efficient, but produce such tiny thrust that accelerating to high speeds would take centuries of continuous operation. Nuclear thermal engines promise higher exhaust velocities, yet they still fall short by orders of magnitude. Even fusion-based designs, which tap into the same process that powers stars, struggle to push beyond a few percent of light speed without becoming absurdly massive. Project studies conducted during the 20th century made this painfully clear. Designs that looked elegant on paper revealed horrifying fuel requirements when numbers were plugged in. Some proposed vehicles would need tens of thousands of tons of fusion fuel just to deliver a small payload to a nearby star over several decades. The engines themselves would be dwarfed by fuel tanks, turning the spacecraft into a fragile, elongated structure vulnerable to failure at countless points. Antimatter propulsion, often portrayed as the ultimate solution, fares little better in practice. While matter-antimatter annihilation is extraordinarily energy-dense, producing antimatter is currently one of the most inefficient processes humans know how to perform. Generating even a few grams requires massive particle accelerators and enormous energy input, and storing it safely demands magnetic containment systems that consume constant power. Scaling this up to interstellar mission levels would require production timelines stretching thousands of years. Solar sails offer an elegant alternative by using light itself as propulsion, but elegance does not translate into speed. The pressure exerted by photons is incredibly weak, and while it can provide continuous acceleration, the rate is so small that meaningful velocities take decades or centuries to achieve. Each of these methods encounters the same wall from a different angle. They all attempt to win a race that the universe has rigged by making the track impossibly long and the finish line unreachable within a human lifetime. What makes this limitation particularly cruel is that it is not a matter of insufficient ingenuity. We are not failing because we lack intelligence or creativity. We are failing because the universe enforces strict bookkeeping on momentum and energy, and that bookkeeping does not care how badly we want to explore. No amount of clever engineering can escape the exponential growth of required fuel mass when using reaction-based propulsion. The problem compounds so quickly that even hypothetical materials and perfect efficiency do not save the day. At some point, the numbers simply stop making sense. This realization has forced physicists and engineers to confront an uncomfortable conclusion. No matter how much we refine rockets, they will never be enough to carry us to the stars in any practical way. Interstellar travel cannot be solved by pushing harder in the same direction. It requires abandoning the idea that speed must come from thrust alone. Until we accept that limitation, we remain stuck optimizing systems that are fundamentally incapable of delivering what we need. The failure of rockets is not a temporary setback on the road to the stars. It is a signpost pointing toward an entirely different way of thinking about motion, energy, and how humanity might one day escape the gravitational pull of its own assumptions. Even if humanity somehow found a way to build engines powerful enough to overcome the fuel problem, an even more absolute barrier waits beyond it, one that does not bend to engineering at all. In the early 20th century, Albert Einstein revealed that space and time are not separate stages on which events unfold, but a single interconnected structure that governs how motion works at the deepest level. His theory of special relativity introduced a rule so fundamental that it reshaped physics forever. Nothing with mass can reach or exceed the speed of light. This is not a technological limitation or a challenge awaiting innovation. It is a built-in constraint of the universe itself. As an object accelerates closer to light speed, its resistance to further acceleration increases dramatically. The energy required does not rise in a linear or even exponential way. It skyrockets toward infinity. Each additional increase in velocity demands disproportionately more energy than the last, until the cost becomes infinite at the light speed threshold. This happens because motion near light speed alters the very relationship between energy, mass, and time. From the universe's perspective, accelerating an object makes it behave as if it were becoming heavier, not in a conventional sense, but in a way that reflects how much energy is locked into its motion. The faster it goes, the more energy it carries, and the harder it becomes to push any faster. This creates a cosmic dead end where no amount of fuel, power, or engineering brilliance can push a massive object across that final boundary. The universe allows approach, but forbids crossing. This speed limit is not theoretical speculation. It has been tested repeatedly and confirmed with unsettling precision. Particle accelerators around the world hurl subatomic particles to speeds just shy of light, and every experiment agrees with Einstein's predictions. The particles become harder to accelerate, their effective mass increases, and time itself slows down relative to the laboratory frame. No experiment has ever observed a massive particle breaking this limit. The rule appears absolute. This realization shattered earlier hopes that interstellar travel might simply be a matter of building faster ships. Instead, it revealed that traditional motion through space is fundamentally capped. Even if a spacecraft could reach 99% of light speed, which itself would require energy rivaling the output of entire civilizations, it would still face staggering travel times across interstellar distances. Worse still, relativity introduces side effects that make such travel deeply alien to human experience. Time dilation means that clocks aboard a near light-speed ship would tick far more slowly than clocks back on Earth. For the travelers, the journey might feel relatively short, but decades or centuries could pass for those left behind. Length contraction adds another layer of strangeness, making distances appear shorter in the direction of travel from the ship's perspective, while remaining unchanged for observers elsewhere. These effects are not illusions or mathematical tricks. They are real, measurable consequences of how space-time behaves at extreme velocities. Together, they create a universe where attempting to outrun light comes with profound penalties even before the ultimate barrier is reached. For generations, Physicists treated this speed limit as the final word. It became foundational knowledge, taught as an unbreakable rule of reality. Faster-than-light travel was categorized alongside perpetual motion machines and time machines, concepts that make for entertaining stories but collapse under serious scrutiny. Attempts to bypass the limit by clever maneuvers or exotic fuels always failed because they misunderstood the nature of the constraint. The issue was never about propulsion efficiency. It was about how space-time itself responds to motion. Breaking the light-speed barrier would not just challenge engineering principles, it would undermine causality, the ordered sequence of cause and effect that gives the universe coherence. If information or matter could travel faster than light, paradoxes would emerge where effects precede their causes, eroding the logical structure that makes physics possible. This threat to causality reinforced the belief that the universe enforces its speed limit to protect its own consistency. The laws of relativity seem to lock humanity into a slow cosmic crawl, allowing exploration only within narrow bounds. Yet within those same equations, subtle hints suggested that the limit applied specifically to motion through space, not necessarily to space itself. For decades, this distinction remained a curiosity rather than a solution, overshadowed by the overwhelming authority of Einstein's speed limit. But as physicists continued to probe the structure of space-time, some began to suspect that the barrier was not as simple as it first appeared, and that the universe might permit shortcuts for those clever enough to find them. Beyond the abstract equations and cosmic speed limits lies a more intimate cost of near-light speed travel, one that strikes at the core of human identity and connection. Relativity does not merely restrict how fast objects can move. It reshapes how time itself is experienced by those who attempt to push against that boundary. As velocity increases, time aboard a fast-moving spacecraft slows relative to the rest of the universe, a phenomenon known as time dilation. At modest speeds, this effect is negligible, but as a ship approaches the speed of light, the difference becomes profound. A journey that feels like a decade to the crew could unfold as a century or more on Earth. This is not a thought experiment or philosophical puzzle. It is a measurable reality confirmed by experiments involving atomic clocks and high-energy particles. The faster you move, the further you drift out of sync with everyone else. For interstellar travelers, this creates a cruel form of isolation. They would leave home knowing that even a successful mission guarantees permanent separation from the world they came from. Families would age, cultures would change, and entire societies could transform beyond recognition during what felt like a single career-length voyage. Returning home would mean arriving in a future where everyone you once knew exists only in archives and memories. This temporal exile makes relativistic travel emotionally and socially devastating, even if it were technically feasible. Some have suggested embracing this consequence through generational missions, where crews accept that they will never return, and that their descendants will complete the journey. Yet this solution replaces one impossibility with another. Sustaining a stable civilization aboard a spacecraft for centuries introduces risks that multiply over time. Social cohesion, governance, resource management, and technological maintenance must remain intact across generations who never consented to the mission. A single cultural shift or loss of institutional knowledge could derail the entire endeavor. The ship itself becomes a fragile ecosystem where failure at any point could mean extinction for everyone aboard. Suspended animation and cryogenic preservation are often proposed as alternatives, but these technologies remain speculative and face fundamental biological obstacles. Freezing complex organisms without causing irreversible cellular damage has not been solved, and even if it were, reviving humans after decades or centuries of isolation raises psychological and ethical questions we are not prepared to answer. Time dilation also distorts causality in subtler ways. Communication between a near light-speed ship and Earth becomes increasingly impractical, as messages sent back and forth lose relevance by the time they arrive. Decisions must be made without guidance, and feedback loops that normally allow societies to adapt and correct course break down. The travelers become disconnected, not just emotionally, but informationally, operating in a temporal bubble detached from the flow of history. This disconnect undermines the very idea of exploration as a shared human endeavor. Exploration traditionally involves returning with knowledge, stories, and discoveries that enrich the originating culture. Relativistic travel turns exploration into a one-way exile, where the benefits may arrive long after the explorers themselves are gone. Even from a purely practical standpoint, time dilation destroys economic viability. No society can invest resources into projects whose outcomes lie centuries in the future, with no possibility of course correction. The mismatch between human decision-making timescales and relativistic travel timelines makes such missions incompatible with how civilizations function. These problems compound the already overwhelming energy and engineering challenges, making near light-speed travel not just difficult, but deeply incompatible with human life as we understand it. The universe, it seems, imposes not only physical barriers, but psychological ones, ensuring that even if we could approach light speed, the cost would be measured in lost generations and broken continuity. This realization has driven physicists to search for alternatives that preserve the human experience of time while still enabling rapid travel. Any viable path to the stars must allow travelers to remain synchronized with the rest of humanity, to leave and return without becoming strangers to their own species. Without that continuity, interstellar travel becomes an academic curiosity rather than a meaningful expansion of human presence. The cruel irony is that relativity, while opening our eyes to the true structure of the universe, also revealed how deeply incompatible conventional high-speed travel is with the rhythms of human life. Only by finding a way to move without paying this temporal price can humanity hope to reach beyond its cradle without losing itself in the process. Even if humanity were willing to accept temporal exile and biological risk, the raw arithmetic of energy delivers a final and nearly merciless verdict. Long before relativity tears travelers away from their own era, the universe demands payment in the only currency that truly matters: energy. To accelerate any object to extreme speeds requires enormous amounts of it. And as velocities climb closer to light speed, those requirements explode beyond comprehension. This is not a matter of inefficient design or immature technology. It is a consequence of how energy and motion are fundamentally linked. A spacecraft weighing only a few tons would require energy comparable to the total annual output of modern civilization just to approach relativistic speeds, and that energy would need to be delivered with near-perfect efficiency in a matter of moments. Stretching the acceleration over longer periods reduces stress on the craft, but does nothing to reduce the total energy required. The bill must be paid regardless of how slowly the check is written. Fusion power, often hailed as humanity's future energy solution, offers only modest relief. While fusion releases vastly more energy per unit mass than chemical fuels, it still falls far short of what interstellar travel demands. Converting entire mountains of fuel into energy would barely move a moderately sized ship to a meaningful fraction of light speed. Even the sun itself, producing unimaginable power every second, could not easily propel a spacecraft across the galaxy within a human lifetime if that energy had to be carried on board. Antimatter appears more promising on paper, as it represents the most efficient conversion of mass to energy allowed by physics, yet practicality quickly crushes that hope. Producing antimatter requires particle accelerators that consume enormous amounts of electricity, and current production rates are measured in nanograms per year. Storing it safely demands complex magnetic traps that themselves require constant energy input. Scaling this technology to interstellar levels would take longer than the age of modern civilization, just to manufacture enough fuel for a single mission. Solar sails avoid fuel entirely, but they trade power for patience. The gentle push of starlight can accelerate a spacecraft indefinitely, yet the force is so weak that reaching even modest fractions of light speed would require decades or centuries of continuous acceleration under ideal conditions. Any deviation, damage, or loss of alignment could erase years of progress. Historical project studies reveal just how bleak the situation becomes when numbers replace optimism. Mid-20th century proposals for fusion-powered starships envisioned vehicles carrying tens of thousands of tons of fuel to deliver payloads weighing only a few hundred tons, and even then, travel times stretched across decades. These designs assumed flawless engineering, uninterrupted operation, and energy sources that humanity has yet to master. They were not blueprints for real missions, but mathematical demonstrations of how unforgiving the energy problem truly is. No matter how powerful the engine, reaction-based propulsion always demands that energy be carried along for the ride, and that requirement alone makes high-speed interstellar travel wildly inefficient. The deeper issue is that energy must do more than accelerate the ship. It must also haul the fuel used to produce that energy. This recursive burden ensures that returns diminish rapidly as ambitions grow. At some point, the added fuel contributes more mass than usable momentum, turning progress into stagnation. Engineers have known this for generations, and it is why no serious propulsion concept based on conventional physics promises anything close to practical interstellar travel. The energy wall stands tall and absolute, indifferent to human dreams and clever designs. It represents not just a technological hurdle, but a fundamental mismatch between what the universe demands and what civilizations can realistically supply. This realization has forced physicists to confront an uncomfortable truth. If reaching the stars requires carrying star-level energy on board, then traditional travel methods are dead ends. Any viable solution must find a way to access vast energy without transporting it, or better yet, avoid paying the energy cost of acceleration altogether. Until that happens, humanity remains bound to slow, incremental expansion, forever aware that the stars are close enough to see, but far too expensive to touch. Confronted with these limits, some argue that humanity does not truly need the stars, that survival and expansion can be achieved within our own solar system. But a closer look reveals how fragile and misleading that hope really is. Every other world circling our sun is hostile to human life in ways that are not merely inconvenient, but fundamentally incompatible with biology as we know it. Mars is often presented as our backup home, yet beneath the romance of red deserts lies a brutal reality. Its atmosphere is so thin that standing on the surface would be equivalent to existing at extreme altitude on Earth without protection, while temperatures routinely plunge far below anything tolerable by unshielded life. Lacking a strong magnetic field, Mars is constantly bombarded by radiation that slowly damages DNA and erodes any atmosphere it tries to hold. Even with advanced technology, transforming Mars into a truly Earth-like environment would require reshaping an entire planet over thousands of years, assuming solutions to problems we do not yet know how to solve. Venus is even less forgiving. Beneath its cloud cover lies a surface hot enough to melt metals, crushed under pressures comparable to deep ocean depths on Earth, wrapped in an atmosphere thick with carbon dioxide and corrosive chemicals. Probes sent there survive only briefly before being destroyed, and no amount of engineering ingenuity can turn such a world into a habitable refuge without essentially rebuilding it from scratch. The giant planets offer no solid ground at all, only crushing layers of gas and violent storms that would tear apart any structure long before it could find stability. Their moons, while intriguing, remain frozen, airless, or bathed in intense radiation. Some harbor subsurface oceans, but accessing them would require drilling through kilometers of ice in environments that would quickly disable even hardened machinery. Mercury swings between scorching heat and extreme cold, while lacking an atmosphere capable of moderating either condition. The Moon, though close and familiar, provides no air, little protection from radiation, and minimal resources to support large populations without constant resupply from Earth. In every case, survival beyond short-term habitation depends on sealed environments that must be maintained indefinitely. These are not new homes. They are outposts clinging to life through continuous technological effort. Terraforming is often invoked as a long-term solution, but this concept remains largely theoretical. Changing a planet's atmosphere, temperature, and magnetic environment requires energy and materials on a scale that rivals planetary formation itself. Even optimistic estimates suggest that making Mars marginally comfortable would take many centuries, and that comfort would still fall far short of Earth's natural balance. During that time, humanity would remain vulnerable to the very threats that motivate expansion in the first place. Earth is not just our birthplace. It is an unusually stable oasis in a universe that offers few comparable havens nearby. Its climate, atmosphere, magnetic field, and liquid water exist in a delicate equilibrium that took billions of years to develop. There is no second Earth waiting within easy reach. This means that all long-term plans for humanity that remain confined to the solar system ultimately circle back to the same fragile dependency on one world. A major asteroid impact, runaway climate change, or unforeseen cosmic event could still threaten civilization despite colonies scattered across nearby planets and moons. Without access to truly independent worlds, humanity's safety margin remains dangerously thin. The uncomfortable conclusion is that the solar system, for all its wonders, does not provide a genuine escape route. It offers exploration, resources, and inspiration, but not redundancy. To secure our future, We need worlds that already possess the conditions for life, or can sustain it with far less intervention than any nearby planet allows. Those worlds exist, but they orbit other stars. Until we can reach them, all talk of humanity's long-term survival remains constrained by a single point of failure. The stars are not a luxury destination. They represent the only realistic path toward resilience on cosmic timescales. Without a way to travel beyond our solar neighborhood, humanity remains a civilization with impressive tools but no true backup, hoping that a planet shaped by chance will continue to protect us indefinitely. The frustration deepens when we realize that the universe has not been stingy with potential new homes. It has placed them tantalizingly close on cosmic scales, while ensuring they remain unreachable on human ones. Over the past few decades, astronomers have confirmed the existence of thousands of planets orbiting distant stars, many of them rocky, Earth-sized, and located in regions where liquid water could exist on their surfaces. These discoveries transformed the search for life from speculation into statistics, revealing that planets like ours are not rare accidents, but common outcomes of star formation. Among these worlds, a few stand out as especially tempting. Proxima Centauri b orbits the star nearest to our own, just over 4 light-years away. A distance that sounds small, until one remembers it represents more than 40 trillion kilometers of empty space. This planet sits within its star's habitable zone, where temperatures could allow liquid water, and early observations suggest it may possess a magnetic field capable of shielding its surface from radiation. It is close enough to feel almost reachable, yet far enough to remain completely inaccessible with any existing spacecraft. The TRAPPIST-1 system offers an even richer promise. Around a cool red dwarf star, 40 light-years away, orbit 7 Earth-sized planets, several of which lie squarely in the habitable zone. Computer models suggest these worlds could host atmospheres, weather patterns, and even oceans, making them prime candidates for life. Then there is Kepler 452b, often described as Earth's cousin, orbiting a star remarkably similar to the Sun at a distance of roughly 1,400 light-years. It receives only slightly more energy than Earth does, placing it within a temperature range that could support life as we understand it. Each of these discoveries sharpens a particular kind of cosmic cruelty. We can measure these worlds with extraordinary precision, determining their mass, size, orbital period, and even hints of atmospheric composition. Yet physically reaching them remains an impossible dream. Telescopes like the James Webb Space Telescope can detect water vapor, carbon dioxide, and other key molecules in alien atmospheres, offering glimpses of climates and chemical cycles unfolding light-years away. In some cases, we may even detect signs that hint at biological processes. And still, these planets might as well exist behind a locked door with no key. Even the nearest candidate, Proxima Centauri b, would require tens of thousands of years to reach using our fastest probes. TRAPPIST-1 would demand hundreds of thousands of years, while more distant Earth-like worlds push travel times into the millions. These numbers stop functioning as travel durations and begin resembling geological eras. By the time a probe arrived, the civilization that launched it would be long gone, its languages forgotten, its purpose unclear even to descendants who might inherit the mission's data. This gap between observation and access creates a unique form of scientific frustration. For the first time in history, humanity can identify specific destinations that could host life, perhaps even intelligent civilizations, yet cannot meaningfully interact with them. We are explorers equipped with maps, but denied the ability to walk the terrain. This limitation also reshapes how we think about discovery itself. Traditionally, exploration involved direct contact. Sailors crossed oceans, scientists trekked to remote regions, and astronauts walked on other worlds. Exoplanet science reverses that pattern, turning exploration into a distant, indirect exercise conducted entirely through photons and mathematics. While powerful, this approach leaves critical questions unanswered. Does life exist there? How complex is it? What ecosystems emerge under different stars? These are questions that remote sensing alone may never fully resolve. The existence of so many potentially habitable planets also intensifies the existential stakes. If Earth becomes uninhabitable, these worlds represent possible refuges, places where humanity could continue its story. Knowing they exist without being able to reach them is like spotting lifeboats drifting just beyond the horizon while stranded at sea. The universe teases us with abundance while enforcing isolation. This is why faster-than-light travel is not a matter of curiosity or prestige. It is the only concept that bridges the widening gap between what we can discover and what we can reach. Without it, the catalogue of habitable worlds will continue to grow, while humanity remains anchored to a single fragile planet, fully aware that alternatives exist, but permanently beyond our grasp. At this point, faster-than-light travel stops being a speculative indulgence and becomes something far more serious, an existential requirement tied directly to humanity's long-term survival. Earth is an extraordinary world, but it is not eternal, and pretending otherwise is a dangerous illusion. Our planet exists within a dynamic and often hostile cosmic environment, where stability is temporary by definition. Asteroid impacts, supervolcanic eruptions, long-term climate shifts, nearby supernovae, and the gradual brightening of the sun all represent genuine threats that operate on timescales far longer than human political systems, but far shorter than the lifespan of the universe. Civilization may survive one or two such challenges, but relying indefinitely on a single planet places all of humanity's future behind a single fragile barrier. History shows that resilience comes from diversification. Species that spread across multiple environments are harder to erase than those confined to one niche, and the same principle applies on a civilizational scale. Without access to other star systems, humanity remains a high-risk experiment balanced on a narrow ledge. Some argue that technological mastery of Earth alone will solve these problems, that climate engineering, asteroid deflection, and planetary management can indefinitely preserve our home. While these efforts are essential, they address symptoms rather than root causes. No matter how advanced our defenses become, a single-planet civilization is vulnerable to rare but catastrophic events beyond its control. True resilience requires redundancy, and redundancy on cosmic timescales demands multiple independent worlds. The uncomfortable truth is that our solar system does not provide this redundancy. Mars, the Moon, and artificial habitats can serve as stepping stones and laboratories, but they remain tethered to Earth's fate in fundamental ways. A catastrophe severe enough to destabilize Earth's biosphere would likely ripple outward, disrupting supply chains, energy systems, and human infrastructure across the solar system. Only by establishing self-sustaining populations around other stars can humanity break free from this shared vulnerability. Faster-than-light travel transforms this necessity from an abstract dream into a practical strategy. Without it, interstellar colonization remains a theoretical exercise detached from human timeframes. With it, entire regions of the galaxy become accessible within years rather than millennia. The difference is not incremental, it is categorical. Faster-than-light capability would redefine what counts as nearby, collapsing cosmic distances into manageable journeys. This shift would allow humanity to treat the galaxy not as an unreachable backdrop, but as an environment that can be explored, settled, and understood directly. It would also fundamentally change how civilizations plan for the future. Long-term projects would no longer be constrained by the assumption that stars are forever out of reach. Exploration, migration, and resource acquisition could occur on timescales compatible with human institutions and decision-making processes. The argument for faster-than-light travel is therefore not rooted in curiosity or conquest, but in continuity. It is about ensuring that human culture, knowledge, and biological diversity do not vanish because of a single unlucky event. There is also a quieter motivation that drives this pursuit: the desire to participate fully in the universe we observe. Humanity has reached a point where our understanding of cosmic processes outpaces our ability to engage with them. We can model stellar evolution, map galactic structure, and detect planets forming around distant stars, yet remain spectators rather than participants. This imbalance creates a tension between what we know and what we can do, a tension that faster-than-light travel promises to resolve. It would allow science to move from observation to experimentation on interstellar scales, transforming astronomy into a hands-on discipline rather than a distant one. Ethical considerations further complicate the picture. If life exists elsewhere, especially complex or intelligent life, remaining isolated forever limits our capacity to understand our place in a living universe. Contact, if it ever occurs, will shape humanity's future regardless of whether we are prepared for it. Developing the ability to travel between stars gives us agency in that process, rather than leaving us passive recipients of whatever signals might eventually reach Earth. Of course, faster-than-light travel introduces its own risks and responsibilities, but refusing to explore because of potential danger has never been a successful survival strategy. Every major expansion in human history carried uncertainty, and yet those expansions shaped who we are today. On a cosmic scale, the choice is similar. Either humanity remains confined to a single world, hoping that chance and caution will protect us indefinitely, or we accept the challenge of overcoming the universe's deepest constraints in order to secure a future among the stars. Faster-than-light travel is not about escaping Earth. It is about ensuring that Earth is not the only place where humanity's story can continue. After confronting the impossibility of conventional solutions, physicists were forced to step back and question an assumption so deeply ingrained that it had gone largely unexamined. The idea that travel must always mean moving an object through space. For centuries, motion was understood as displacement, a body changing position relative to its surroundings. Ships crossed oceans by cutting through water, aircraft pierced the air, and spacecraft blasted through vacuum by throwing mass behind them. Every form of transportation humanity ever invented followed this same intuitive pattern. But relativity quietly introduced a radical alternative by revealing that space itself is not a passive backdrop. It can stretch, compress, bend, and ripple. Space is not merely where motion happens. It is something that can move and change in its own right. This insight opened a door that had been hiding in plain sight. If the universe limits how fast objects can travel through space, it says nothing about how fast space itself may rearrange. In fact, cosmology already provides an astonishing example of this distinction. During the early moments after the Big Bang, the universe expanded at a rate far exceeding the speed of light, carrying galaxies away from one another faster than any signal could chase them. Even today, distant regions of the cosmos recede from us faster than light due to the ongoing expansion of space. This does not violate relativity because nothing locally moves faster than light. It is space itself that stretches. Once this difference is understood, the entire problem of interstellar travel begins to look different. Instead of asking how to accelerate a ship to impossible speeds, a new question emerges. What if the ship could remain essentially stationary while space around it does the moving? This reframing is subtle but profound. It shifts the challenge away from propulsion and toward geometry, from engines to space-time manipulation. Rather than fighting the universe's speed limit head-on, it suggests slipping around it by exploiting how space-time behaves on large scales. This idea feels counterintuitive because human intuition evolved in a world where space appears rigid and unchanging. We experience it as an empty stage, not as a dynamic substance. Yet every experiment in modern physics tells us that this perception is incomplete. Gravity itself is not a force pulling objects together, but a consequence of space-time curvature guiding motion. Massive bodies tell space how to bend, and space tells matter how to move. If mass can warp space-time unintentionally, then perhaps advanced technology could warp it deliberately. This is the conceptual leap that marks the transition from science fiction to serious theoretical physics. Instead of propelling a spacecraft faster and faster, one could imagine creating a region of space-time that carries the craft along, much like a conveyor belt embedded in the fabric of the universe. The ship would not outrun light locally. It would simply be transported by a moving geometry. Inside this region, the familiar rules of motion would still apply. Clocks would tick normally, bodies would experience no crushing forces, and the crew would not feel acceleration. All the extreme effects associated with near light-speed travel would occur outside the region, in the surrounding space-time that is being reshaped. This approach transforms the problem from one of brute force into one of precision control. Instead of requiring infinite energy to push matter past a forbidden speed, it requires the ability to engineer space-time itself. That is still an extraordinary challenge, but it is no longer mathematically forbidden. The universe, it turns out, does not prohibit all forms of faster-than-light motion. It only forbids certain kinds. Recognizing this distinction was like realizing that a locked door has an open window. You cannot fort your way through the door, but the building was never truly sealed. This realization also changes how physicists think about progress. Traditional propulsion improvements offer diminishing returns, but space-time manipulation promises exponential ones. A small change in geometry could produce enormous effective velocities without subjecting travelers to extreme conditions. The challenge becomes learning how to shape space-time reliably, predictably, and safely. That requires understanding not just relativity, but how it interfaces with quantum physics, energy distributions, and the vacuum itself. At this stage, the idea remains abstract. But abstraction is where all revolutions in physics begin. The key point is that the universe has already demonstrated the behavior we would need. It expands, contracts, and distorts space on cosmic scales all the time. The question is no longer whether such motion is possible, but whether intelligent beings can learn to reproduce it on demand. This shift in perspective marks the true beginning of the faster-than-light discussion, not as a fantasy of speed, but as a proposal to rethink what movement actually means in a universe where space itself is alive and mutable. The moment this conceptual shift took shape, it demanded a concrete mathematical test, and that test arrived in the mid-1990s when a young physicist decided to take the idea seriously rather than dismiss it as fantasy. Miguel Alcubierre, then a graduate student, asked a simple but audacious question. If space-time can expand and contract, could it be shaped in a way that allows effective faster-than-light travel without violating Einstein's equations? Instead of speculating, he did what physicists do best and turned to mathematics. In 1994, he published a solution to the equations of general relativity that stunned the scientific community, not because it was speculative, but because it was technically valid. His model described a region of space-time shaped like a bubble, inside which a spacecraft could reside. In front of this bubble, space-time would be compressed, shortening the distance to the destination, while behind it, space-time would expand, stretching the distance already traveled. The bubble itself would move forward as a result of this asymmetry, carrying the spacecraft along like a surfer riding a wave. Crucially, the ship inside the bubble would not be moving through space-time in the traditional sense at all. Locally, it would remain stationary, floating in a calm pocket of normal physics while the universe rearranged itself around it. This detail mattered more than anything else, because it meant the ship never violated the speed of light within its own frame of reference. Einstein's limit remained intact locally, even as the bubble achieved an effective velocity far exceeding light speed relative to distant observers. Alcubierre's solution did not break relativity, it exploited it. That distinction forced physicists to reconsider assumptions they had treated as absolute. The equations of general relativity had quietly allowed this possibility all along, hidden in their flexibility. Nothing in the math explicitly forbade space-time from being sculpted in this way. For decades, faster-than-light travel had been dismissed because it was assumed to require accelerating matter past a universal limit. Alcubierre showed that acceleration was not required at all. The ship could sit still, while space-time itself did the moving. This was not a modification of Einstein's theory or a loophole discovered through hand-waving. It was a legitimate solution derived directly from accepted physics. Predictably, skepticism followed immediately. Many physicists assumed there must be a hidden flaw, some overlooked instability or contradiction that would render the idea meaningless. But as researchers examined the equations, the solution held up. It did not violate causality in any obvious way. It did not require imaginary dimensions or untested forces. It was strange, yes, but no stranger than black holes or gravitational waves once seemed. What ultimately tempered enthusiasm was not mathematical illegitimacy, but practicality. Alcubierre's original calculations revealed that generating such a warp bubble would require exotic conditions far beyond anything humanity could achieve. The energy needed to warp space-time in this manner was enormous, and worse, it appeared to require a form of energy unlike anything normally found in nature. Still, the significance of the breakthrough couldn't be ignored. For the first time, faster-than-light travel had been placed on a scientific footing. It was no longer a narrative device or speculative dream. It was a well-defined geometry of space-time with equations that could be analyzed, modified, and optimized. Alcubierre himself did not claim he had invented a practical propulsion system. He viewed his work as an exploration of what relativity allowed, not a blueprint for engineers. Yet the implications were unavoidable. If space-time could be shaped this way in theory, then the universe itself did not prohibit effective faster-than-light motion. The door was open, even if what lay beyond it looked impossibly difficult to reach. The warp bubble concept reframed the entire discussion. Instead of asking how fast a ship could go, physicists now asked how space-time could be engineered. Instead of focusing on engines and fuel, they began thinking in terms of energy distributions, curvature tensors, and vacuum dynamics. The challenge shifted from propulsion to geometry. While Alcubierre's original model raised as many questions as it answered, it achieved something rare in physics. It transformed a forbidden idea into a permitted one. Faster-than-light travel was no longer ruled out by principle, only by practicality. That distinction made all the difference, because practicality changes over time, while principles do not. Once an idea survives contact with fundamental physics, it becomes a target for refinement rather than rejection. Alcubierre's paper marked the moment when warp travel stepped out of fiction and into the uncomfortable, tantalizing realm of real science, where impossibility is no longer assumed, only deferred. To understand why the warp bubble concept was so disruptive, it helps to examine what life inside such a structure would actually be like. Because its most radical feature is not speed, but normality. Inside the bubble described by Alcubierre's equations, space-time remains flat and undisturbed, meaning the laws of physics behave exactly as they do on Earth. There is no sensation of acceleration, no crushing forces, no relativistic distortions affecting clocks or bodies. A crew member could stand, walk, eat, sleep, and conduct experiments without noticing anything unusual, even while the bubble itself moves at many times the speed of light relative to the outside universe. This occurs because the ship is not being accelerated through space. Instead, space ahead of the bubble is continuously compressed while space behind it is stretched, creating a moving region of distorted geometry that carries the ship along. The effect is analogous to standing on a moving walkway in an airport. You are not running faster than your legs allow, yet you still reach your destination more quickly because the ground beneath you is doing the work. The implications of this are extraordinary. All the brutal side effects of conventional high-speed travel disappear. Time dilation no longer separates travelers from their home era, because time inside the bubble flows at the same rate as time outside. A journey to a nearby star system could take weeks for the crew and weeks for observers back on Earth. There is no twin paradox, no temporal exile, no generational disconnect. Likewise, the problem of lethal acceleration vanishes entirely. Because the ship itself does not change velocity in its local frame, the crew experiences zero inertial stress. You could, in principle, go from rest to extreme effective speeds instantly without any physical sensation. The universe absorbs the violence of motion at the bubble boundary, not inside the ship. This makes warp travel not only fast, but biologically compatible in a way no other interstellar concept can match. Fragile equipment, living organisms, and complex systems could all be transported without special reinforcement or suspension. From the crew's perspective, the journey would feel no more dangerous than remaining docked in orbit. The strangeness emerges only when considering how the bubble interacts with the external universe. To outside observers, the warp bubble would appear as a region of extreme space-time distortion, potentially cloaked from view by the very geometry that enables its motion. Light in front of the bubble would be severely blue-shifted, compressed into higher energies, while light behind would be stretched into longer wavelengths. This could make the bubble effectively invisible or highly distorted when viewed from afar. Communication across the bubble boundary becomes problematic as well. Signals attempting to exit or enter the bubble must cross regions of rapidly changing space-time curvature, which may block or scramble electromagnetic transmission entirely. This suggests that warp travel could involve periods of complete isolation, where the crew is cut off from external contact until the bubble collapses at the destination. Navigation presents another challenge. With the external universe distorted, traditional visual guidance becomes unreliable, forcing reliance on pre-computed trajectories and internal sensors capable of interpreting warped space-time metrics. Yet even these challenges highlight how fundamentally different warp travel is from anything previously imagined. It does not ask humans to endure extreme conditions. It asks engineers to master extreme geometry. The bubble acts as a shield, protecting its contents from radiation, micrometeoroids, and even violent cosmic events. In theory, a warp bubble could pass through environments that would instantly destroy conventional spacecraft, while remaining completely unaffected inside. This protective quality further reinforces why the concept captured scientific attention. It solves multiple problems simultaneously: speed, time, acceleration, and environmental hazard. The cost is complexity rather than sacrifice. Instead of pushing crews to their physical and psychological limits, warp travel demands unprecedented precision in controlling space-time itself. This shift in burden is what makes the idea so appealing and so daunting. The challenge is no longer whether humans can survive the journey, but whether humanity can learn to sculpt the universe with sufficient finesse. Warp bubbles turn interstellar travel from a test of endurance into a test of understanding. If space-time can be shaped reliably, then the stars cease to be distant prisons and become reachable destinations within a lifetime. The ride itself would feel deceptively ordinary, even as it rewrites what motion means at a fundamental level. As elegant as the warp bubble concept appears on paper, it collides headfirst with a requirement that initially seemed to doom it to impossibility: the need for a form of energy that behaves in the exact opposite way to everything we are familiar with. Alcubierre's original solution demanded regions of space-time filled with what physicists call negative energy density, a condition where energy is lower than that of empty space itself. This is not antimatter, which still carries positive mass and energy, but something far stranger, a substance that would curve space-time outward rather than inward. Ordinary matter creates gravitational wells that attract objects and bend space-time like a heavy weight on fabric. Exotic matter, by contrast, would create gravitational hills, pushing space-time away and enabling the contraction and expansion pattern required for a warp bubble. The problem is that no such material has ever been observed in nature. Every particle ever detected from electrons to galaxies, possesses positive energy. Negative energy appears to exist only as a mathematical possibility within the equations of relativity. This immediately raised alarms. Physics allows many solutions that describe universes very different from our own, but nature does not realize all of them. The fact that negative energy solutions exist on paper does not guarantee they can exist in reality. Even worse, Alcubierre's initial calculations suggested that the quantity required would be absurdly large. To generate a warp bubble large enough to hold a modest spacecraft, the amount of negative energy needed was comparable to the total mass energy of a giant planet. Converting something like Jupiter into exotic matter, assuming that were even possible, would require energy far beyond anything humanity could ever hope to command. This staggering requirement became the primary argument against warp drives. Critics acknowledged that the mathematics was correct, but dismissed the idea as physically meaningless because it depended on ingredients that seemed entirely fictional. In this view, warp drives belonged in the same category as perfectly rigid materials or infinite density objects, allowed by equations but forbidden by reality. The negative energy problem also raised deeper theoretical concerns. Large regions of negative energy could destabilize space-time, potentially allowing violations of causality or the formation of closed time-like curves, where time loops back on itself. Quantum field theory includes energy conditions that appear to prohibit sustained negative energy over macroscopic scales, acting as safeguards against such paradoxes. These conditions suggest that while tiny, fleeting negative energy effects might exist, nature strongly resists their amplification. This reinforced the belief that warp drives were clever mathematical curiosities rather than viable technologies. Yet physics has a long history of overturning assumptions once considered absolute. Before the 20th century, empty space was thought to contain nothing at all. Before quantum mechanics, the idea that particles could appear and disappear spontaneously would have seemed absurd. The exotic matter problem, while severe, did not technically violate any known laws. It merely challenged our understanding of what forms energy could take. This distinction kept the idea alive at the fringes of serious research. Some physicists began asking whether negative energy truly required a new form of matter, or whether known physical phenomena could produce the same effect under the right conditions. If space-time responds to energy density rather than specific particles, then perhaps manipulating energy distributions could mimic exotic matter without requiring entirely new substances. This line of thinking reframed the problem. Instead of searching for impossible materials, researchers began exploring whether the vacuum itself could be engineered to behave differently. The universe's emptiest regions are not truly empty. They seethe with quantum activity. If that activity could be altered, perhaps negative energy could be produced indirectly. While these ideas were speculative, they provided a path forward that did not rely on discovering alien matter types. The exotic matter problem thus became less of a dead end and more of a challenge statement. If warp drives were ever to move beyond theory, physics would need to uncover new ways to manipulate energy at the deepest level. What initially looked like a fatal flaw gradually transformed into the central puzzle driving further investigation. Rather than ending the discussion, the requirement for negative energy forced researchers to dig deeper into the nature of the vacuum, space-time stability, and the hidden flexibility of physical law. In doing so, It kept the dream of warp travel alive, not as fantasy, but as an unresolved question waiting for a breakthrough. The first real crack in the exotic matter barrier emerged from an unexpected place, not from distant galaxies or hypothetical particles, but from the strange behavior of empty space itself. Modern physics has revealed that the vacuum is anything but void. It is a restless ocean of quantum fluctuations where virtual particles constantly flicker into and out of existence. These particles borrow energy from uncertainty, exist for unimaginably brief moments, and then vanish before the universe demands repayment. Under normal conditions, this quantum activity balances out evenly, producing no observable force. But in the late 1940s, physicist Hendrik Casimir predicted that this balance could be disrupted under the right circumstances. When two uncharged metal plates are placed extremely close together in a vacuum, only certain quantum wavelengths can exist in the narrow gap between them, while all wavelengths remain free to appear outside. This imbalance creates a measurable pressure difference, pushing the plates toward each other. The result, now known as the Casimir effect, is a real, experimentally verified force arising purely from altered vacuum energy. What makes this phenomenon so important for warp physics is not the force itself, but what it represents. The energy density between the plates is lower than that of the surrounding vacuum. Relative to normal empty space, this region possesses negative energy density. It is small, fleeting, and tightly constrained, but it is real. For the first time, physics demonstrated that negative energy is not purely theoretical. It can exist under specific quantum conditions. This discovery reframed the warp drive problem in a profound way. Exotic matter might not be required after all if negative energy could be generated by manipulating the vacuum rather than introducing new particles. The Casimir effect showed that space-time responds to energy differences, not labels. If energy density could be reduced locally, space-time curvature would respond accordingly. Of course, the effect as observed in laboratories is incredibly weak. The plates must be separated by distances smaller than the width of a human hair, and the resulting force is tiny. Scaling this effect up from nanometers to meters appears almost absurd. The force drops off rapidly as distance increases, and maintaining such configurations requires extreme precision. Yet the significance lies not in practicality, but in possibility. The universe permits negative energy under certain conditions, and that alone dismantles the claim that warp drives require fundamentally impossible ingredients. Researchers began exploring whether Casimir-like effects could be amplified, shaped, or layered to produce more substantial space-time distortions. Instead of two flat plates, what if complex geometries were used? What if oscillating fields could sustain negative energy regions dynamically? What if multiple effects could resonate, reinforcing one another the way small vibrations combine into powerful waves? These questions opened an entirely new research direction focused on engineering the vacuum itself. Rather than searching for exotic matter, scientists began asking how empty space could be persuaded to behave in exotic ways. This approach aligned naturally with advances in materials, science, and quantum engineering. Metamaterials, artificially structured substances designed to manipulate electromagnetic fields in unusual ways, became potential tools for shaping vacuum energy distributions. By controlling how fields propagate at microscopic scales, such materials might influence which quantum fluctuations are allowed to exist in a given region. While speculative, this idea connected warp physics to active research areas rather than imaginary substances. The Casimir effect also forced physicists to confront the limits imposed by quantum field theory. Negative energy can exist, but only under strict constraints. It cannot be arbitrarily large or sustained indefinitely without triggering compensating positive energy elsewhere. This suggests that if warp bubbles are possible, they must be carefully balanced systems rather than brute force distortions. The universe appears to tolerate small violations of intuitive energy behavior, but only when they are paid back elsewhere. Understanding and exploiting this accounting system becomes the central challenge. The Casimir effect did not solve the warp drive problem, but it transformed it. What once seemed to require fictional matter now appeared to demand unprecedented control over known physics. That shift changed the tone of the discussion from dismissal to cautious curiosity. If negative energy could be coaxed from the vacuum, then the barrier between theory and experiment was no longer absolute. The problem moved from "this cannot exist" to "we do not yet know how to build it," a subtle but critical difference that marked the moment warp drive research began inching towards the laboratory rather than remaining trapped on the page. The transition from abstract possibility to experimental curiosity occurred when a small group of physicists decided to stop debating whether warp-like space-time distortions could exist and instead try to measure them directly. Among them was Harold White, a propulsion physicist working within NASA who believed the Alcubierre concept deserved more than theoretical dismissal. Rather than attempting to build a warp drive outright, White focused on a far more modest goal: determine whether space-time could be measurably distorted in a laboratory setting using known physical effects. His work centered on refining the mathematics of warp bubbles and exploring whether their energy requirements had been misunderstood. By carefully re-examining the geometry of the original Alcubierre solution, White discovered that the extreme energy demands were not fixed. They depended heavily on the shape and thickness of the warp bubble itself. Small changes in geometry produced dramatic reductions in required energy, suggesting that the original estimates were far from optimal. This realization alone reignited serious interest in the concept, as it showed that warp physics was not a binary problem of impossible versus possible, but a continuum where clever design mattered. White proposed alternative bubble configurations that distributed space-time curvature more efficiently, reducing peak energy densities by orders of magnitude. While still enormous, these requirements dropped from planetary scales to something approaching engineering imagination. The real turning point came when White and his team began experimenting with vacuum energy effects, particularly those related to the Casimir phenomenon. Using specialized equipment designed to detect extremely small space-time distortions, they explored whether manipulating electromagnetic fields and vacuum boundaries could produce measurable geometric changes. These experiments were never intended to propel anything. They were designed to test whether the underlying physics behaved as theory predicted. During these investigations, the team observed something remarkable: tiny, repeatable distortions consistent with warp-like space-time geometry at microscopic scales. The effect was unimaginably small, many orders of magnitude below what would be required for propulsion, but its significance was enormous. For the first time, warp bubble geometry was not just a mathematical construct, but a measurable physical phenomenon. The laboratory had produced a minuscule analog of the space-time behavior described by Alcubierre decades earlier, This did not mean a warp drive had been built, but it did mean that space-time could be shaped deliberately, even if only slightly, using known physics. The implications were profound. Warp geometry had crossed a threshold from theoretical allowance to experimental observation. Critics were quick to urge caution, pointing out that nanoscopic effects do not automatically scale to macroscopic systems. Many alternative explanations were proposed, including experimental noise or misinterpreted electromagnetic interactions. Yet the consistency of the results and their alignment with theoretical predictions made them difficult to dismiss outright. White's work demonstrated that the vacuum is not a rigid background, but a medium that can be influenced in subtle ways. This realization changed the tone of warp research dramatically. What had once been considered speculative fantasy began to resemble early-stage experimental science. Funding agencies took notice, and the conversation shifted from whether warp physics violated known laws to how far those laws could be pushed. The laboratory results suggested that the universe does not outright forbid warp-like distortions. It merely makes them extraordinarily difficult to produce at meaningful scales. This distinction is crucial. Technologies often begin with effects so small, they seem useless until someone discovers how to amplify them. Electricity, nuclear reactions, and lasers all followed this trajectory, starting as curiosities before transforming civilization. White's experiments placed warp physics at the very beginning of a similar path. The challenge ahead was no longer to prove that space-time could be warped, but to understand how such warping might be strengthened, stabilized, and controlled. The appearance of a warp-like effect in a controlled environment marked a psychological breakthrough as much as a scientific one. It signaled that humanity was no longer discussing warp travel purely in the language of imagination. Instead, it had taken its first tentative steps toward treating space-time as something that could, at least in principle, be engineered. Once laboratory-scale space-time distortion was shown to be possible, even in the faintest form, the focus of warp research shifted decisively toward optimization rather than proof. Physicists began asking not whether warp geometry could exist, but how it could be reshaped to reduce its extreme demands. One of the most important insights to emerge was that the original spherical warp bubble proposed by Alcubierre was mathematically convenient but physically inefficient. Its sharp boundaries required intense concentrations of negative energy, making the design fragile and energetically expensive. By altering the geometry of the bubble, those requirements could be softened. One promising modification involved reshaping the bubble into a toroidal or ring-like configuration that distributed space-time curvature more evenly. Instead of forcing space-time to bend abruptly, the toroidal design allowed curvature to flow smoothly around the ship, dramatically lowering peak energy densities. Additional refinements showed that allowing the bubble's boundary to oscillate rather than remain static could further reduce energy demands by preventing extreme buildup at any single point. These oscillations function like controlled ripples rather than rigid walls, maintaining the warp effect while easing structural stress on space-time itself. Parallel to these efforts, other researchers explored alternative warp models altogether. José Notario proposed a different solution to Einstein's equations that eliminated the need for expanding and contracting space in the same way as Alcubierre's original concept. Instead, The Natario configuration relies on a more subtle redistribution of space-time curvature that produces motion without requiring sharp discontinuities. This approach appealed to physicists concerned about stability, as smoother curvature transitions are less likely to trigger quantum instabilities or unwanted radiation effects. While the Natario model did not eliminate the need for exotic energy conditions, it suggested that warp motion could be achieved with gentler manipulations of spacetime, potentially making real-world implementation more feasible. Some teams began experimenting with hybrid models that combined features from both approaches, using Alcubierre-style compression for efficiency, while adopting Natario-style smoothness for stability. Each variation represented an attempt to tame space-time rather than force it into submission. As computational power increased, supercomputer simulations allowed researchers to test millions of configurations, adjusting parameters like bubble thickness, curvature gradients, and energy distribution patterns. Many designs failed catastrophically in simulation, collapsing or producing runaway effects. But others revealed narrow corridors of stability where warp geometry could theoretically persist with reduced energy input. These results reinforced a crucial lesson. Warp physics is highly sensitive to geometry. Small changes in shape can mean the difference between infinite energy requirements and merely astronomical ones. This sensitivity suggests that the original prohibitive estimates were not fundamental barriers, but consequences of inefficient designs. Another major avenue of optimization involved the idea of pulsed warp fields. Instead of maintaining a continuous space-time distortion, some models propose creating brief, repeating warp pulses that nudge a vessel forward incrementally. This approach mirrors how engines operate in cycles rather than producing constant output. By allowing space-time to relax between pulses, the system could avoid the accumulation of extreme energy densities. While this would reduce top speed, it could dramatically lower power requirements, making early warp prototypes more achievable. As these ideas evolved, the narrative around warp drives began to change. What once seemed to require godlike power now appeared to demand exceptional precision. The challenge was no longer sheer magnitude, but control. Engineers would need to shape energy distributions with extraordinary accuracy, synchronizing fields in ways never before attempted. This places warp research at the intersection of relativity, quantum physics, and advanced control theory. Each optimization step did not bring warp travel close to deployment, but it steadily moved it away from the realm of impossibility. The energy requirements, though still immense, became finite and quantifiable, rather than infinite and absurd. That shift matters because history shows that finite problems eventually yield to sustained effort. Optimizing warp geometry transformed the concept from a single fragile idea into a family of potential solutions, each with its own trade-offs and challenges. This diversity increased the odds that at least one configuration might prove viable under real-world constraints. Warp drives were no longer a monolithic dream, but an evolving design space where progress could be measured, refined, and built upon step by step. As warp drive theory matured from isolated equations into a growing family of models, some researchers began wondering whether humanity might not be the first civilization to confront these challenges, and whether the universe itself might already contain evidence of others who succeeded. If warp bubbles distort space-time, then their motion should leave detectable fingerprints, subtle but unmistakable ripples propagating outward at the speed of light. These ripples would take the form of gravitational waves, disturbances in space-time similar to those produced by colliding black holes or neutron stars, but with a very different structure. Unlike natural astrophysical events, a moving warp bubble would generate a persistent, directional signature shaped by its geometry, speed, and duration of travel. This idea led physicists to a provocative question. If advanced civilizations are using warp-like technology, could we detect their passage by listening to space-time itself? With the advent of gravitational wave observatories such as LIGO and Virgo, humanity gained the ability to measure distortions thousands of times smaller than a proton, opening a new sensory channel to the universe. Researchers began modeling what an artificial space-time distortion would look like to these detectors, simulating warp bubbles of various sizes and configurations. The results were striking. Warp-driven motion would produce gravitational wave patterns unlike any known natural source, featuring asymmetries, sustained frequency bands, and polarization signatures that could not be easily mimicked by black hole mergers or stellar explosions. These simulations suggested that if a sufficiently powerful warp system operated within a few thousand light-years of Earth, current or near-future detectors might already be capable of noticing it. This transformed the search for faster-than-light travel into an observational science rather than a purely theoretical one. Scientists started combing through existing gravitational wave data, not expecting immediate confirmation, but looking for unexplained anomalies that resisted conventional interpretation. So far, no definitive evidence of artificial space-time manipulation has been found, but the search itself has only just begun. Gravitational wave astronomy is still in its infancy, with sensitivity and resolution improving every year. Future observatories, both ground-based and spaceborne, will be capable of detecting fainter and more complex signals, expanding the volume of space we can monitor dramatically. The implications of a detection would be staggering. Even a single confirmed artificial warp signature would instantly prove that faster-than-light travel is physically achievable, ending decades of debate in one moment. It would also imply the existence of a technologically advanced civilization somewhere in our cosmic neighborhood, raising profound questions about our place in the universe. Such a discovery would not provide blueprints, but it would offer something just as valuable: an existence proof. Knowing that warp travel works in practice would accelerate human research by eliminating entire classes of doubt. Scientists could reverse engineer the observed signatures, inferring bubble geometry, energy distribution, and operational behavior from the gravitational wave patterns alone. This process mirrors how astronomers deduce the properties of distant stars and black holes from the light and radiation they emit. Even without direct contact, the universe itself would become a laboratory, showcasing successful warp engineering. Of course, skeptics caution that advanced civilizations might deliberately minimize detectable signatures, using optimized geometries or shielding techniques to avoid broadcasting their presence. Yet perfection is rare, and even cautious travelers could leave traces during emergencies, early development stages, or rare maneuvers. Moreover, ancient warp events could still echo through space-time long after the civilizations that created them vanished. The search is not limited to gravitational waves alone. The interaction between a warp bubble and interstellar matter could produce unusual radiation signatures, energetic particle bursts, or localized distortions in starlight. Astronomers are beginning to catalog unexplained phenomena with these possibilities in mind, re-examining anomalies that were once dismissed as noise. While none have yet crossed the threshold into convincing evidence, the methodology itself represents a shift in perspective. Humanity is no longer asking only how to build a warp drive, but how to recognize one if it already exists. This dual approach, building while listening, increases the odds of progress. Either we invent faster-than-light travel ourselves, or we discover that the universe already contains examples to learn from. In both cases, the silence or signals of space-time carry information. The act of listening turns the cosmos into a potential archive of advanced technology, written not in metal or code, but in the geometry of reality itself. The possibility of faster-than-light motion inevitably revives one of physics's most unsettling fears: the idea that breaking the light barrier could unravel causality itself. According to relativity, space and time are intertwined in such a way that observers moving relative to one another can disagree on the order of events. When speeds remain below light, these disagreements never become paradoxical. Cause always precedes effect in every reference frame. But once faster-than-light travel enters the picture, mathematics allows scenarios where an object could arrive at a destination before it appears to have left, at least from certain perspectives. This opens the door to logical contradictions that challenge the coherence of reality, famously illustrated by time travel paradoxes, where events cancel their own causes. For decades, this threat has been used as a decisive argument against faster-than-light physics. Many theorists believe the universe must forbid such motion because a reality that permits paradoxes cannot remain consistent. Stephen Hawking formalized this intuition in his chronology protection conjecture, proposing that unknown physical mechanisms arise to prevent time travel whenever it threatens causality. According to this view, the universe acts like a self-correcting system, allowing strange behavior only up to the point where logical consistency is endangered. Warp drives, however, occupy a peculiar gray zone within this debate. Unlike hypothetical engines that propel matter directly faster than light, warp bubbles isolate their interior from external reference frames. The ship inside does not outrun light locally, and no signal travels through space-time faster than light in its immediate surroundings. Instead, space-time itself is reshaped, raising the possibility that causality violations might be avoided rather than triggered. Some theoretical analyses suggest that information cannot propagate backward through a warp bubble, because the bubble's boundary acts as a causal barrier. Signals attempting to cross from inside to outside, or vice versa, must pass through regions of extreme space-time curvature that enforce one-way information flow. In this interpretation, warp drives permit rapid displacement without enabling communication into the past. The universe preserves causality by design, even while allowing effective superluminal travel. Another safeguard may arise from the energetic cost of maintaining a warp field. Warp bubbles require continuous energy input to sustain their geometry. Once that input stops, the bubble collapses. This creates an inherent arrow of time, as energy must be supplied in the present to maintain the structure. You cannot retroactively power a warp field that already exists, preventing closed loops where causes originate from their own effects. Some physicists argue that this alone is sufficient to block time travel paradoxes. More speculative ideas invoke the structure of quantum mechanics itself. In interpretations where reality branches into multiple histories, actions that appear to change the past simply create new timelines rather than altering the original one. In this view, faster-than-light travel does not break causality, but redistributes it across parallel outcomes. While such interpretations remain controversial, they highlight the possibility that the universe has deeper mechanisms for maintaining consistency than classical intuition suggests. Importantly, none of these arguments are settled. They represent attempts to understand how faster-than-light motion might coexist with a causal universe, not proofs that it can. The only definitive way to resolve the issue would be experimental evidence, either from human-built warp systems or from detected signatures of extraterrestrial ones. If the universe truly forbids faster-than-light travel, attempts to build warp drives may encounter unexpected instabilities or failures that reinforce chronology protection. If not, then the absence of paradoxes in real-world operation would reveal that our understanding of causality has been incomplete. Either outcome would represent a profound advance in physics. The fear of paradoxes, while legitimate, cannot serve as a reason to halt inquiry. Many concepts once thought impossible or dangerous, from nuclear reactions to black holes, turned out to be real and governed by rules that preserve cosmic order. Warp drives may belong to the same category, appearing threatening only because they challenge deeply held assumptions. Whether the universe ultimately allows such motion or not, exploring the question forces us to confront the foundations of time, cause, and reality itself. In that sense, warp research is not merely about travel, but about understanding why the universe behaves consistently at all. As these theoretical debates unfold, warp research has quietly transitioned from academic curiosity into a strategic pursuit, drawing the attention of governments, private corporations, and defense institutions that recognize its transformative potential. Publicly, most space agencies maintain cautious language, framing faster-than-light concepts as distant possibilities best left to speculative research. Privately, however, the picture appears far more complex. Within organizations like NASA, small but persistent research groups have continued investigating advanced propulsion concepts under carefully worded mandates. These efforts focus not on building starships, but on probing the limits of space-time manipulation, vacuum energy control, and high-precision field dynamics. Such research is often buried within broader programs to avoid attracting controversy, yet its persistence suggests long-term institutional interest. Military organizations have even stronger incentives. A technology capable of reshaping space-time would render traditional notions of distance, defense, and deterrence obsolete. Even the hint of such capability motivates classified research programs, where secrecy is justified by national security concerns. History shows that revolutionary technologies rarely emerge in the open. They are developed quietly until their implications can no longer be contained. Beyond government labs, private industry has entered the race with a different mindset. Companies driven by long-term vision rather than short-term return are increasingly willing to fund speculative physics research. Organizations involved in space launch, satellite networks, and advanced materials science employ physicists whose work extends far beyond improving chemical rockets. Job postings, patent filings, and research collaborations hint at investigations into exotic propulsion, high-energy field manipulation, and space-time engineering, even if specifics remain undisclosed. Private funding offers advantages that government programs often lack: faster iteration, greater tolerance for failure, and fewer bureaucratic constraints. This makes it well-suited for exploring unconventional ideas that might never survive traditional review processes. At the same time, the absence of transparency complicates assessment of progress. Breakthroughs achieved in private or classified environments may remain hidden for years, creating a gap between public perception and actual capability. This uncertainty fuels speculation, but it also reflects a genuine race where information itself becomes a strategic asset. International cooperation, once a hallmark of space exploration, struggles to adapt to this new reality. While basic research is still shared through academic channels, anything approaching practical application is increasingly siloed. No nation wants to risk falling behind in a domain that could redefine power on a planetary scale. This competitive dynamic accelerates investment, but discourages openness, slowing collective understanding even as individual efforts intensify. Outside traditional aerospace sectors, interdisciplinary teams are emerging that combine expertise in quantum computing, materials science, and artificial intelligence. Warp research demands unprecedented coordination across these fields, as controlling space-time geometry requires real-time calculation, adaptive feedback, and materials capable of withstanding extreme conditions. AI-driven optimization and simulation play a growing role, allowing researchers to explore design spaces far too vast for human intuition alone. These tools can identify configurations that balance energy efficiency, stability, and control, narrowing the path toward viable prototypes. The result is a fragmented but vigorous ecosystem of research, advancing unevenly but persistently. Some groups focus on fundamental physics, others on experimental validation, and still others on enabling technologies that may not be labeled as warp research at all. Together, they form an invisible infrastructure pushing against the boundaries of what is known. From the outside, progress appears slow, but history suggests that transformative technologies often incubate quietly before emerging suddenly. The first successful demonstration of powered flight followed decades of failed attempts and obscure experiments. Nuclear energy leapt from theoretical insight to world-altering reality in less than a decade once conditions aligned. Warp technology may follow a similar pattern, appearing stagnant until a critical threshold is crossed. The question is no longer whether anyone is trying, but who will succeed first and under what circumstances. The pursuit of warp capability has become a silent contest, not just between nations, but between visions of the future. Will faster-than-light travel emerge as a shared human achievement, or as a guarded tool of power? The answer depends not only on physics, but on choices being made right now in laboratories, boardrooms, and classified facilities around the world. If humanity ever succeeds in mastering warp travel, the consequences will extend far beyond faster ships or shorter journeys. They will redefine what civilization itself means. Distances that once dictated isolation will collapse, turning nearby stars into reachable destinations and transforming the galaxy from an abstract map into a lived environment. Worlds that today exist only as data points in astronomical catalogs would become places with landscapes, histories, and ecosystems that can be studied directly. Colonization would no longer require generational sacrifice or irreversible separation from Earth. Human communities could spread outward while remaining culturally and temporally connected, exchanging knowledge, people, and ideas across interstellar distances as easily as nations once exchanged ships across oceans. This continuity would preserve shared identity while allowing diversity to flourish, creating a civilization distributed across multiple stars, yet unified by communication and travel times, measured in weeks rather than centuries. The scientific impact alone would be revolutionary. Direct exploration would replace inference, enabling experiments in environments impossible to recreate on Earth. Stellar interiors, extreme gravitational fields, and alien biospheres could be observed up close, rewriting entire fields of knowledge. The search for life would shift from passive listening to active discovery, and the question of whether humanity is alone would likely be answered not by distant signals, but by direct encounter. Economically, warp travel would unlock resources on scales that dwarf anything available within a single solar system. Asteroids, gas giants, and entire star systems could be accessed, reshaping energy production, manufacturing, and wealth distribution. Such abundance carries risks as well as promise, demanding new frameworks to prevent exploitation and conflict. Ethical challenges would multiply as well. Encountering life elsewhere would force humanity to confront its responsibilities beyond Earth. Decisions about non-interference, cooperation, and coexistence would shape not just our future, but the future of other worlds. Even uninhabited planets would raise questions about stewardship and preservation. The ability to reach the stars would not grant moral clarity, it would demand it. At the same time, warp technology introduces dangers that cannot be ignored. The potential for misuse, whether as a weapon or a tool of domination, looms large. A civilization capable of reshaping space-time must also learn to restrain itself. Environmental consequences remain uncertain. If warp travel alters space-time locally, repeated use could have cumulative effects we do not yet understand. Safeguards, monitoring, and international agreements would be essential to prevent unintended damage to the cosmic environment. Psychologically, humanity would undergo a profound shift. Knowing that the stars are accessible changes how people perceive their lives, their planet, and their place in the universe. Earth would no longer feel like the entirety of existence, but like one home among many. This perspective could foster humility and cooperation, or it could intensify competition and fragmentation. The outcome would depend on how deliberately society prepares for such a transition. Importantly, even the pursuit of warp travel shapes humanity, regardless of whether it ultimately succeeds. The effort pushes physics, engineering, and philosophy into new territory, generating technologies and insights that ripple outward into countless applications. History shows that striving for the seemingly impossible often yields transformative byproducts long before the original goal is reached. Warp research forces us to ask what limits are real and which are artifacts of perspective. It challenges us to confront the nature of space, time, and causality, not as abstractions, but as elements that might one day be shaped by human intention. Whether warp drives become practical in decades or remain elusive for centuries, the direction is clear. Humanity is no longer content to accept cosmic confinement as inevitable. The stars have moved from myth to measurement, and now from measurement to ambition. The next chapters of this story will be written by those willing to question assumptions and explore the deepest structures of reality. If the universe allows us to bend space-time, even slightly, then the age of isolation will end, and humanity's story will expand outward, not as conquerors of the cosmos, but as participants within it.